So we've talked about circuits with resistors, we've talked about circuits with capacitors. Now we're going to talk about what happens when we put both of those circuit elements into a single circuit. And so the simplest way we can do that, of course, is connect a resistor and capacitor in series with a battery. And so here we've got a switch, and what we'll do is at t equals 0, we'll close the switch. And at that instant, our capacitor, because it doesn't have any charge built up on it yet, our capacitor is going to act like a wire, and so we'll have current that will start to flow around the circuit. Now, as that current flows around the circuit, it's going to end up charging the capacitor. And so if we think about our loop rule, so let's start down here in our corner, and we'll go clockwise around our loop. And so again, we're going from the negative to positive terminal across the battery, so we're going to have a voltage increase as we come across the battery in this direction. We're going to go across the resistor with the current, so that's going to be a voltage decrease. And again, we're going to go from this will be the positive terminal of the capacitor to the negatively charged side of the capacitor. So we're going to go from positive to negative across the capacitor. So again, that'll be a voltage decrease. And what that tells us is that the voltage we pick up coming across the battery in this direction has got to be basically canceled out by the drops we get going across the resistor and capacitor. We can calculate what the voltage of the resistor is by using Ohm's law, and the only thing we're going to do is denote the current here with a lowercase I because it's going to change. We can also think about the voltage across the capacitor by using our fundamental relationship for capacitors. So this is just Q equals VC, where we solved it for Q and plugged that in. And again, we've got a lowercase q here because the charge on our capacitor is going to change. So this is up until now we've been dealing with steady state circuits where things didn't change. Here we have here we have a circuit where things are changing. So that's what our lowercase values are telling us. Notice the voltage of the battery, that doesn't change. The resistance of the resistor, that doesn't change. Capacitance of the capacitor, that doesn't change. It's just our current in the circuit and charge built up on the capacitor that does. So how that changes is actually given by a very particular equation. And so the current as a function of time is given by I naught, and this is just the initial current in the circuit, times this exponentially decaying function. So what we see here is that the current decays in the circuit as charge builds up on the capacitor. So this plot down here is showing us the current as a function of time. And so a couple things that are clearly evident from the plot. One is that at t equals 0, we're starting with a current of I naught. We'll come back and talk about what that I naught is in a second. But then as time goes on and charge builds up on our capacitor, the current drops off so that when we get to very large values of t, there's effectively no current flowing through the circuit anymore. Now, one of the things that we can do, right, so this what's going on depends on time, and so one of the things that we can do is we can define what's known as a time constant, and we'll use, so this is the lowercase Greek letter tau. And then we're putting a C on this because we'll come back and talk about a second time constant called the inductive time constant, and this is our capacitive time constant. So our tau sub C is just telling us we're talking about the time constant in an RC circuit when we've got a capacitor. And so you notice that basically tau, our time constant, is just R times C. And so we can rewrite our function for the current is again I naught, what the initial value of the current is, times e to the minus t, so this is our time in seconds, over the time constant. So it works out that our time constant, R times c, actually has units of seconds. And in fact, what the time constant is trying to tell us about, one way to think about it is that 1 tau is the time it takes for 62 or 63.2% of the final charge that we're going to have accumulated on the capacitor to have built up. Another way to think about it in terms of the current, so you see how down here we've basically plotted this in time in terms of 1-time constant, 2-time constants, 3, 4, 5-time constants. And so part of what you can see in our graph of the current is that when it gets to 1-time constant, that the current has dropped to 36.8% of its initial value. So we've now got 63.2% of the charge built up on the capacitor, and our current has dropped to 36.8% of what it started as. So one of the things that we'll pay attention to in our RC circuits is the time constant, because it's going to give us an indication of how quickly will our capacitor charge. Notice when you get past about 5 time constants, effectively you don't have any current left within your circuit. So this is why we really need to see what's going to go on in terms of as our capacitor is charging. That happens relatively quickly. And so by the time we get to 5 time constants, basically our capacitor will be fully charged. So we've said that at t equals 0, our capacitor acts like a wire. So this is going to give us a chance to come back and figure out what this initial current value is. So if it's acting like a wire, basically at t equals 0, this is what our circuit looks like. So because there's no charge built up yet on the capacitor, it acts like a wire, and so effectively at t equals 0, at the instant I close my circuit, I simply have 2 elements, the battery and the resistor. Well, of course, using my loop rule then, at t equals 0 seconds, this tells me that whatever I gain across the battery has to be dropped across the resistor, which means that the initial current flowing through the circuit has got to be equal to the value of the battery divided by the value of the resistor. So the voltage of the battery over the voltage of the resistor is going to tell me what my initial current value is. So I'm going to start at t equals 0 with a current value that's equal to V over R. So this I naught, again, I can figure that out in terms of the other elements in my circuit, the voltage of the battery and the resistance of the resistor. So we'll often rewrite our equation for the current as a function of time as V over R times e to the negative t over RC. Or again, maybe we choose to write that RC as our time constant time. The other thing that's interesting about all this is, of course, if basically no current's flowing after about 5 time constants, so as our time gets really large, basically what that means is our capacitor acts like a broken wire. So it stops current from flowing through once it's fully charged. So an uncharged capacitor acts like a wire. A fully charged capacitor acts like a broken wire. And then what we're keeping track of with this equation is how the capacitor transitions from being a wire to a broken wire over about 5 time constants. So the other parameters that we might be interested in keeping track of. So one of them, of course, is the voltage across the resistor. Well, the voltage across the resistor, we know, is from Ohm's law, is just going to be the current times the resistance of the resistor. And our current changes, so we just plug in I naught times e to the negative t over RC. So this gives us a way to calculate our voltage, where again, we're just using the same time constant within the circuit. So if I go to plot the voltage as a function of time, the voltage of my resistor, at t equals 0, the voltage across the resistor is equal to the voltage of the battery, right? Because that's when my capacitor is acting like a wire. But as t becomes really large, there's no current flowing across my resistor anymore, so there's no voltage across my resistor. So basically, in the same way that the current is decaying in the circuit, the voltage across the resistor is also decaying. By the time you get past about 5 time constants, there's no voltage drop across the resistor anymore because there's no current left flowing through it. So I can think of that time constant as, again, it's 63.2% of the final charge is accumulated on the capacitor. But I can also think of it as, well, now what it's telling me is One time constant is going to be the time it takes for the voltage across my resistor to have dropped to 36.8% of its initial value. And again, in our simple circuit where we just have a battery, a resistor, and a capacitor, that initial value is just the voltage of the battery. So I can also think about the voltage across my capacitor. And again, from my loop rule, I know that the voltage across the battery has got to be basically canceled out by the voltage drop across the resistor and capacitor. So I can solve this equation, my loop rule, solve it for the voltage across the capacitor. And what I get is basically I can factor out AV, and I'm left with this expression. So notice the voltage of the resistor, that's this curve that we were looking at before. The voltage across the resistor decays as the current decreases in the circuit. The voltage across the capacitor increases. So as we place more and more charge onto the capacitor, the voltage across the capacitor increases. And so at t equals 0, there's no charge yet on the capacitor, so there's no voltage across it. No voltage between the capacitor plates. At one time constant, then again I've built up to where I've got 63.2% of the final charge that I'm going to have on my capacitor. So I'm up to 63.2% of the maximum capacitance, or the maximum voltage that I'm going to have between my capacitor plates. And then as T becomes really large, now the voltage across my capacitor is equal to the voltage of the battery. So as the voltage decreases across the resistor, it increases across the capacitor. Well, I can relate the voltage across the capacitor to the charge on the capacitor by using my fundamental relations for capacitors. So this is just Q equals CV, where again I'm saying that Q can change because because the voltage across the capacitor changes. And so when I plug in my equation for the voltage across the capacitor, here it is. And so I get this equation for calculating the charge across my capacitor. And so what I notice is, as t gets really large, this exponential term basically becomes 0. And so I'm left with just CV. And so that's the expression for the maximum charge on the capacitor plates. So in the same way that we said the maximum current flowing through my circuit is just going to be V over R, right? The voltage of the battery divided by the resistance of the resistor. The maximum charge on the capacitor is going to be given by C times V. So the capacitance of my capacitor times the voltage of the battery. And again, our time constant tells us how much we've built up 63.2% of that final charge. No charge at t equals 0, 63.2% of the final value of one time constant, and then we have a fully charged capacitor as t gets really large. So to summarize all this, right? So basically what we're doing is we're saying we're taking our simple RC circuit, we're closing a switch, and then from our loop rule we know that the voltage across the battery, the voltage of the battery has got to be equal to the voltage across the resistor plus the voltage across the capacitor. We can use Ohm's law to calculate one of these, the fundamental relation for our capacitance, for our capacitor to calculate the other. And what we notice as we charge our capacitor up is that the current decreases so that this voltage across the resistor decreases, while the charge on the capacitor increases so the voltage across the capacitor increases. So as the current drops, here's the little dotted line here in this particular plot is the drop of the current. So as the current drops, the charge across the capacitor increases. Here's the equation giving us the charge on the capacitor. Here's the equation giving us the current in the circuit. Again, one of the things we'll pay attention to is what's going on at t equals 0 and what's going on as t becomes very large. And at t equals 0, we know we have no charge on the capacitor, which means we have no voltage across the capacitor. And the current within the circuit is at its maximum value. It's given by the voltage of the battery divided by the resistance of the resistor. As t becomes really large, on the other hand, now I have the maximum charge on the capacitor, that's equal to C times V, so the capacitance of the capacitor times the voltage of the battery. The voltage of the capacitor is equal to the voltage of the battery. So basically the reason current has stopped flowing, or one way to think about it, one way to think about the fact that the current has stopped flowing is because I have two things that effectively act like batteries, the battery over here and my fully charged capacitor over there, but because of the polarity of the battery and the capacitor, they're trying to drive current in two different directions. The battery is trying to drive it clockwise, the fully charged capacitor is trying to drive it counterclockwise. So I end up with no current in my circuit. So this is how we charge capacitors. Now, of course, we can discharge capacitors, which basically means if I take a fully charged capacitor, and now notice I don't need a battery anymore because the fully charged capacitor is going to generate a potential difference to drive my current. So I don't have a battery anymore, I simply have a capacitor and a resistor. When I close my switch in this case, what I see is that the voltage across the capacitor, the current in the circuit, and the charge, all of them follow the same decay curve. So the voltage across the capacitor is equal to the voltage in the resistor in this case. The charge on the capacitor, the current in the circuit, all of them fall off like some number out front times e to the minus t over RC. And RC is our capacitive time constant. So depending on which one of these curves you're interested in, the voltage across the capacitor, the charge, or the current, the maximum value that you start with will either be the original voltage on the capacitor, or the original charge on the capacitor, or the maximum current flowing through the circuit. So all three of these curves, if I'm discharging, look the same. They all have the same functional form. They all exponentially decay by this e to the negative t over RC equation. So that's both charging our capacitor and then discharging our capacitor. And so that's the first of our circuits where things are changing that we'll talk